In section 5.5, we're going to talk about alternating series. So we're going to talk about the alternating series test, and we're going to talk about absolute and conditional convergence. So let's start by defining what an alternating series is. So an alternating series is a series that alternate between positive and negative values. So you either have like positive, negative, or negative, positive. So the general form for it looks like this. I either have -1 to the n plus 1. This is where you have negatives for your even terms, or you have -1 to the n where you have negatives with your odd terms. And it's multiplied by a certain sequence b of n. So let's look at an example of an alternating series. If I have like -1/2 plus 1/4, -1/8 plus 1/16, negative, and so on. So you're going to get the summation of -1/2 to the n. So that's an alternating series because you're going from negative, positive, and so on. Now, the alternating series test is a test to determine if a series is convergence or divergence, but it's limited to when you have -1 to the n or -1 to the n plus 1 in your series. So it's a test for only for a series that looks like that. So this test holds or proves the convergence if two conditions are met. First of all, my b of n, which is the thing multiplied by your -1, must be decreasing. So your bn plus 1 is less than bn. So your terms are becoming smaller. And the limit of this bn is equal to 0. So if these two conditions hold, then your series is convergent. If one of these conditions is not there, this means that we need to do further investigation to determine whether my series is convergent or divergent. It doesn't mean that my series diverges. It just means that I need to use a different test to test my series. So for example, if I have this series, -1 to the n plus 1 times n over 2 to the n, so my bn here is n over 2 to the n. And it's decreasing because n plus 1 over 2 to the n plus 1 is less than or equal to n over n plus 2, because here my denominator is increasing in a faster rate of my numerator. So if the denominator is becoming bigger in a fast way, this means my fraction is becoming smaller in a faster way. So that's why it's decreasing. Now, so the first condition holds. Let's test the second condition. I want to test if the limit is equal to 0. Now, if you do the L'Hopital's rule, you're going to get a 0. So since both of these conditions are met, this means by the alternating tests, we have this series to be convergent. So that's it. So let's assume that I did some calculations and this limit is 1. So if this limit is 1 is not equal to 0, I can't say that this series diverges. It just means that I need to go to a different test to determine whether my series is convergent or divergent. Okay, so now let's define what it means for an absolute and conditional convergence. We say that a series is absolute convergent if I take the same series but with an absolute value and that series converges. And I say that my series is conditionally convergent if my series is convergent, but once I take the absolute value of my sequence inside of the series, it diverges. So it's all about the absolute value. Now, if my series is absolutely convergent, this means my series is convergent. So if the summation of the absolute value converges, this means that my original series converges. So let's look at this example. If I have Oh, absolute conversions could be helpful when we're dealing with alternating series, because sometimes if the alternating series test fails, once you take the absolute value of your alternating series, the negative one is going to disappear, and you're going to get a series that you can apply regular tests to. So if you use the absolute value and you got a convergence series, this means that your original series, which is an alternating series, also converges. If it fails, this means that we need to do more tests and so on. Okay, so let's look at this alternating series. And I want to identify whether it converges absolutely, conditionally, or if it diverges. The first step when we want to identify the type of convergence is taking an absolute value. So once you take an absolute value for your alternating series here, you're going to get n over 2n cubed plus 1. Now, if you look at it, you can tell that I can compare it to the 1 over n squared. So using the comparison test, since n over 2n cubed plus 1 is less than n over 2n cubed, because I'm making the denominator smaller, which is equal to 1 over 2n squared. Now this is using the p-series test, converges. Now since the bigger series converges, by the comparison test, the smaller series converges. Now since this converges using the comparison test, then my original series is absolutely convergent. Because the summation of a to the n of absolute value converges, then it's absolutely convergent, which means that this converges regularly. Now, if we got a divergent value here, I don't know whether my series converges or no. I just know that it does not converge absolutely. But I need to do further testing to determine whether my series converges or diverges. And if it converges, then it would converge conditionally then. Okay, so that's it for this section. You can do these problems and go to Lumen Homework 4 and finish the last 4 problems from it.